This next section is about equilibrium, the final destination of all reactions, or an entertaining science fiction movie starring Christian Bale. We've already discussed this reaction of hydroxide with methyl iodide to produce methanol and iodide. The reaction coordinate diagram is shown below. For this reaction, it is much easier to go forward than to go in reverse. So we say that the energy of activation forward is less than the energy of activation reverse. We also say that the rate constant forward is greater than the rate constant reverse. So if we start with reactants, initially the rate forward is greater than the rate reverse, so the reaction proceeds in the forward direction. If we start with reactants, initially the rate forward is greater than the rate reverse. However, what happens as the concentration of reactants go down and the concentration of products build up? Well, the forward rate slows and the reverse rate speeds up until we reach a special condition known as equilibrium, where the rate forward is equal to the rate reverse. It's also known as the time when the free energy change of the reaction is at zero. Here we have our rate constants and our rate expressions for the forward and the reverse reaction. Notice that for the forward reaction, it is the forward rate constant times the reactants raised to their coefficients. And for the reverse rate, it is the reverse rate constant times the products raised to their coefficient. At equilibrium, the forward rate is equal to the reverse rate. So I will use the rate expressions to substitute for rate forward and rate reverse. Now I will do a little rearranging of the terms and define a new term, capital K, known as the equilibrium constant. Notice that capital K is either the rate constant forward over the rate constant reverse, or products raised to their coefficients over reactants raised to their coefficients. Let's do a little exercise to understand equilibrium. We have reactant in equilibrium with product. We're going to start with 24 tokens or molecules as the reactant and no tokens as the product. Our rate constant forward is going to be 1/3 tokens. That means 0.33 tokens per minute. Our rate constant reverse is going to be 1/5 tokens. That would be a reverse rate constant of 0.2 tokens per minute. Now, since the rate constant forward is greater than the rate constant reverse, I already know that the reaction coordinate diagram looks like the one in the upper right, where we are going downhill from reactants to products. For this exercise, we're going to work with whole numbers, discard fractions, and round down. So here we are, 24 tokens on the reactant side, no tokens on the product side. All right, 1/3 of the tokens are going to go forward. So hopefully you know that 1/3 of 24 is 8. 1/5 of the tokens are going to go in reverse. 1/5 of nothing is still nothing. So here's our new arrangement. 8 tokens went forward, no tokens came in reverse, so now our new ratio of reactants to products is 16 to 8. This is 1 minute into the reaction. Let's go 2 minutes into the reaction. 1/3 of 16 rounds down to 5. So 5 tokens are going to go forward. 1/5 of 8 rounds down to 1. So 1 token is going to go in reverse. 5 forward, 1 reverse. What are the new totals? The new totals are 12 and 12. Now you might think we're at equilibrium because we have equal numbers of products and reactants. But this is not the case. Equilibrium is defined when the rate forward is equal to the rate reverse. So let's keep going into the third minute. 1/3 of 12 is 4 tokens going forward. 1/5 of 12 is going to be 2 tokens going in reverse. So 4 forward, 2 reverse. Here are our new totals. Now we have 10 tokens in the reactant and 14 tokens in the product. Let's go another minute. 1/3 of 10 going forward would be 3 tokens. 1/5 of 14 going in reverse would be 2. Remember, we're rounding down. So 3 forward, 2 reverse. Now the new totals are 9 and 15. All right, for the rest of this exercise, I could keep all day long, and hopefully you'd realize, 1/3 of 9. That'd be 3 going forward. 1/5 of 15. That would be 3 going in reverse. Well, the amounts aren't going to change after this. The amounts at 20 minutes are going to be the same as the amounts at 5 minutes. We are stuck at 9 tokens reactant, 15 tokens product. That's what equilibrium is. The rate forward equals the rate reverse. Here are the actual tallies, and as you can see, the rate that was reversed got faster from 0 to 3, and the rate forward got slower from 8 to 3, until the rate forward equals the rate reverse. Now maybe you think, well, this can't happen again. Why don't we try this with 24 product tokens and no reactant tokens, and see if the number comes out the same. Shall we? Okay, 1/3 of nothing forward would still be nothing, and 1/5 of 24 reverse and rounded down would be 4. So 0 forward, 4 reverse. What are the new totals? 4 and 20. Okay, 1/3 of 4 is 1. 1/5 of 20 is 4. So now, for this second minute, 1 forward, 4 reverse. What are the new totals? 7 and 17. Now for minute 3. 1/3 of 7 is 2. 1/5 of 17 is going to be 3. 2 forward, 3 reverse. Now we are at 8 and 16. Okay, minute 4. 1/3 of 8, that is going to be 2. Remember, we round down. And 1/5 of 16 will be 3 going in reverse. So 2 forward, 3 reverse. And what are the new totals? The same as we were before. 9 reactant tokens and 15 product tokens. And I can continue this for 20 minutes, and the ratio will still be the same. Notice that in this scenario, the rate forward got faster to 3, and the rate reverse got slower to 3, until we reached equilibrium, where the forward rate is equal to the reverse rate. Okay, a couple more things about equilibrium. The equilibrium constant for this reaction, if we take products over reactants, should be 15 over 9. So that is 1.67. But there's another definition of the equilibrium constant. It is the forward rate constant over the reverse rate constant. So that would be 0.33 over 0.2, which is, guess what? 1.67. All right, so this reaction likes to settle such that we have 9 tokens on the reactant side and 15 tokens on the product side. Remember that Mother Nature favors the low energy side. So if we have 24 tokens, more of them would like to be on the low energy side. But she also likes to spread energy out. Remember, she likes entropy. So with any extra energy we have, we're going to put some tokens at the higher energy in order to spread out the energy. And we wind up with equilibrium. Notice that the free energy change at standard state is negative for this reaction, and it settles at which point the free energy change is equal to 0. So at equilibrium for this diagram, the concentration of reactants is less than the concentration of products, which means our equilibrium constant is greater than 1. So when the free energy change at standard state is negative, the equilibrium constant is greater than 1. One way you can relate free energy change to free energy change at standard state is to use a reaction composition diagram. This is the formula where you can use the free energy change at standard state and a slight adjustment to give us the absolute free energy of the system. So in this reaction composition diagram, we start with reactants at a higher energy than products. Here we are at 100% reactant on the left side and 100% product on the right side. Imagine a string that goes from reactant to product, but is a little bit on the droopy side, so it's allowed to sag in the middle. Now, because the platforms are not at the same height, the lowest point of this curve is closer to the product side. In fact, the lowest point of the curve, where the free energy change is 0, is at equilibrium. If we think of the free energy change of the system as the slope, which is the rise over the run, when we are in this region, to the left of the equilibrium point, notice that the slope is negative. So the free energy change is negative. That means the reaction goes forward and is spontaneous under this set of conditions. If we were silly enough to start the reaction with the composition on the right side of the diagram here, notice that going forward would give us a positive slope, meaning the reaction is non-spontaneous in the forward direction, but is spontaneous in the reverse direction. If you were to consider a ball that you rolled down this diagram, where would it settle? It would settle at the lowest point, which is equilibrium. And at this point, with the tangent of this slope, the free energy change of the reaction is 0. Okay, how do we write equilibrium expressions? The general formula is products raised to their coefficient over reactants raised to the coefficient. The same inclusion rules as for rate expressions are applied. Aqueous materials are present in units of moles per liter. Solids are given an activity of 1. Liquids are given an activity of 1. And gases are included either as the pressure of the gas or the concentration of the gas in units of moles per liter. So for this reaction shown, if I were to write the equilibrium expression, it would be products over reactants, but only including the aqueous and gaseous materials. So, for the products, it's fine to include sodium 1 plus and square it because the coefficient in front of the sodium is 2. It's fine to include hydroxide and square it because a coefficient of 2 is in front of the hydroxide. And it's fine to include H2 to the first power, either as a concentration or as a pressure. However, when we consider the reactants, notice they are in solid or liquid state, so they have activities of 1. The equilibrium expression for this reaction is the one shown below. Here's a typical Chem 101 question. What is the equilibrium expression for the reaction shown? Remember, it is products raised to their coefficient over reactants raised to their coefficient, but only gases and aqueous materials apply. So, I do believe this would be SO2 squared. So, that gives me either choice 1 or choice 2. And then reactants should be H2S squared and O2 cubed. And these are multiplied together. So I do believe the proper answer for this question is 2. This question asks us to write the equilibrium expression when calcium phosphate dissolves. Alright, if we think about what our products are right here, we're going to have calcium ion, so that would be calcium 2 plus, and there will be 3 of them. So that would be calcium 2 plus cubed. There will also be 2 phosphate ions that are in aqueous solution, so it should be phosphate squared. These would be my products, and my reactants, well, solids have an activity of 1. So I can't use answer 2 or 3 because these include the solid. I do believe the answer to this question is probably 1. Here's an actual calculation problem. We are given the equilibrium value of 7.5 times 10 to the minus 5, and we'd like to know what is the calcium ion concentration that exists in equilibrium if hydronium is 0.23 molar and HF is 0.88 molar. Alright, let us start by writing the equilibrium expression, which hopefully you believe is calcium 2 plus to the first power, HF squared, not water because it's liquid, not calcium fluoride because it's solid, but over hydronium squared. This is the equilibrium expression. We would like to find the calcium concentration. So let me rearrange that so we have calcium 2 plus on one side and the rest of the terms on the other. Now it's just a matter of substituting these values in. I have the value of K, I have the hydronium concentration, I have the hydrofluoric acid concentration. So I will put those in my calculator, and I find that the calcium 2 plus ion concentration is 5.1 times 10 to the minus 6th molar. This question asks us to get the concentration of chloride in a solution where we are 0.110 molar in lead ion, and also we've added 0.230 moles of lead chloride to 1 liter of solution. Alright, once again we should probably start by writing the equilibrium expression. So, K is equal to lead 2 plus times chloride squared over 1. If I rearrange this so that I have chloride on this side, I should use the equilibrium constant, which is given here, 1.7 times 10 to the minus 5, divided by the lead 2 plus concentration here, which is 0.110. Now, this will give me the chloride concentration squared. In order to solve for this, hopefully you realize that we need to just take the square root of K divided by lead. This question gives us the concentrations of materials and asks us to get the equilibrium constant. So, hopefully again you think of the expression. The expression should be the acetate times the hydronium divided by the acetic acid. So we would take the acetate, which is 1.33 times 10 to the minus 3, times the hydronium, which is the same value, divided by the acetic acid concentration, which is 0.0990 molar. And I hope that when you put that into your calculator, you have decided that the answer is very close to 2. So to summarize this, here are the 3 different types of reaction coordinate diagrams. We can either go uphill from reactant to product, have the same energy, or go downhill from reactant to product. And if we think of having 10 molecules in the reaction and recognize that the lower energy side is preferred, for the first diagram, we might wind up with more reactant than product. So the equilibrium constant for that kind of diagram will be less than 1 and favor reactant. For the next diagram, both reactant and product are at the same energy. So neither one is preferred, and we would have counters of 5 and 5. So this is a diagram for which the equilibrium constant is equal to 1. Finally, the last diagram, the product is preferred. So, as equilibrium is products over reactants, this would give us an equilibrium constant that is greater than 1 and mostly prefers product. Here's one last question for you. If the initial reactant concentration is 1 molar, which diagram represents product being at mostly 1 molar at equilibrium? In order to answer this question, we need to sort of think in terms of reactant diagrams. Initially, reactant is 1 molar and we have no product. In order for the reaction to occur, we are going to subtract X for reactant and add X for product. In order for the product concentration to be close to 1 molar at equilibrium, that means that this reaction must go forward very well, such that the product is close to 1 molar and the reactant is close to 0. Which one of these diagrams says to you, make a lot of product and don't have very much reactant? I'm hoping you think the answer is C. This concludes this lecture on equilibrium.